Okay, welcome everybody to the first session of contributed talks for the Haskell Symposium. As always, these talks are all live streamed. If you have any questions, especially for the online audience, please submit them on Discord, not the YouTube channel comments. And yeah, Minh is going to talk to us about effect handlers for programmable inference. So please take it away.
Thank you. Hi. Hear me okay?
Yeah.
Right. Okay, so today I'm going to talk about using Haskell to improve probabilistic programming languages. Or in other words, I'm going to use Haskell to trick you into learning statistics. Okay, so what is a probabilistic programming language? So there are tools for inferring missing data. So there are two main steps to using one of these. First, the programmer writes a model which expresses a problem in terms of random variables. Then use an inference algorithm to learn the relationships between these variables. So let's take the following problem. Given some input x, we can see this generates a data point y according to a noisy line mx plus c. So I'll use the normal distribution to express this noise. Because we can observe what values of y are, this is known as an observable variable. We also have our suspicion about how the slope and intercepts are distributed. But because these aren't tangible values that we can see, these are latent variables. Okay, so what I've effectively done is model our problem in terms of the variables we know about and those we wish to learn. If you were to write this as a program, let's say in Anglican, it looked like this. So there are two key operations that we need. The sample operations describe how we think M and C are distributed. The observe operation then says, given some random samples of M and C, what's the likelihood of them having generated Y? Now, an important detail to note is that sample and observe don't actually do anything yet. And that's because in probabilistic programming, we want to separate the model from the inference algorithm. So the model is just syntax. It describes a problem we want to learn. By later providing semantics to sample and observe, we can implement different algorithms that learn M and C. So how is this done in practice? Well, in Anglican, models are first compiled into continuation passing style. The user is then given a library of algorithms that can execute the model by interpreting sample and observe. Now, while this framework is very straightforward to use, what if you wanted to build your own algorithm? Well, this is difficult. The model is now in a very low-level representation, and each algorithm comes packaged as this black box procedure. So one alternative is a language called Gen. So here, you're given an interface of methods for interacting with the model. By then combining these in different ways, you can then implement your own algorithm as a regular function, which is great because functions are super modular. However, the interface itself is fixed. So this means you can't program how the model executes, which in turn limits how you can program inference. So let's instead consider Perera then. Here, algorithms are coroutines that you can program yourself. But like the other languages, the approach still isn't typed. So this means there's nothing restricting what sample and observe should do, and nothing telling us what information they pass. So it's easy to have one bad coroutine corrupt the entire algorithm. So these 3 points I've listed are all different but important aspects of inference programming. That is our ability to customize existing algorithms and build new ones out of smaller parts. However, most languages for inference are often limited in at least one aspect. So in this talk, I'm going to use Haskell and Algebraic Effects as a way of proposing a new approach to inference programming. Okay, so last year in ICFP, we developed a language in Haskell for modeling based on algebraic effects. And in this, you can write linear regression like this. So sample takes a distribution D that generates values of type A, and it gives us a sample from it. Observe is similar, except it also takes an observed value to condition against. So as this is the minimal interface you would need to write a model, you can think of them as having the following types. That is, they are programs that can perform observing and sampling side effects, as well as I/O. And this type prog is where the algebraic effects comes in, and it's how we capture models as syntax. So to demonstrate, if we were to desugar this model, we'd get the following tree. So the nodes of the tree are the op constructors, which have two arguments. The first is a specific operation belonging to one of the program's effects. The second argument is a continuation. It takes the operation's result and it gives us the rest of the tree. And finally, the leaves of the tree are the val constructors containing the output of our program. Okay, so using algebraic effects, we've captured these models as trees. We can then assign semantics to our trees by using effect handlers. So given a program that has E as its first effect, a handler interprets all the operations of type E, giving us back a program where that effect has been removed. So by handling all the effects in our program, we can fully execute it. So for instance, let's just define a handler for sample that just draws random samples. So if we pattern match on sample, we'll get a random value R between 0 and 1. And then by passing it to draw, we deterministically draw a sample from that distribution. In the last line, we'll then apply the continuation K to the result, which gives us the rest of a program which we recursively handle. In the val case, we've reached the end of the program, and so we return the result. And then, likewise, we can define a handler for observe. So here, I'm just going to compute the log probability of each observation and return the sum of these at the end. If we then compose these two handlers, we implement a very simple algorithm called likelihood weighting. So if I were to run this on linear regression at the top, we'd get back a list of weighted samples for M and C, where the values for M equals 3 and C equals 0 have a higher weight, which are the actual values I use to generate the data. Okay, so using algebraic effects, I've given you the following framework. The model is a program that contains abstract operations, sample and observe. The inference algorithm then handles these operations, executing the model thousands of times and generating some values that we care about. Now, while this was fine for the likelihood weighting algorithm I just showed you, practical real-world algorithms are much more complex with lots of moving parts. So these algorithms not only provide a semantics for the model, but they come with their own procedures and side effects that happen outside of the model. And this framework simply isn't modular enough to capture these details nicely. So we need a more fine-grained way of programming inference, something that consolidates what the algorithms have in common and lets us derive new variants easily. Well, the key insight of this talk is that we can do this by viewing inference in the exact same way that we viewed models. In particular, we can think of certain families or patterns of inference also as programs with their own abstract operations. By making them abstract, it can actually be clearer what an algorithm is trying to do. So for instance, one pattern of inference is Metropolis-Hastings, whose key operations are proposing new samples and deciding whether to accept these proposals. another family of algorithms are particle filters, whose key operation is resampling. To then derive a concrete algorithm from the framework, as the programmer, you need to provide two things. You need to give a semantics for the model operations, like usual, but also a semantics for the inference operations. So to show you how to use this framework, let me first explain what an inference pattern looks like. So we'll start off with Metropolis-Hastings. So Metropolis-Hastings begins with this tuple here, which you can think of as the configuration of the model. The important part is tau of type trace. So this is the sample trace of a model, and it lets us provide values for each random choice it makes. So by giving a model a large enough trace, you can execute it deterministically. The W is then a weight, and it measures how likely a model execution is to produce our observations. And finally, the X is the output. So in linear regression, this was the M and C that we were trying to learn. We then begin the algorithm by applying MH step. So the idea is that we're going to propose new configurations and decide whether to accept them by comparing with the most recent one. And over time, we'll build up a chain of these. So each step begins by getting the most recent one. Then we'll call propose. This takes our old sample trace and it generates a new one for us to try out. Exec is then a model interpreter. It executes our model under a given trace and it returns us a resulting configuration. And then finally, we'll call accept, which compares our new configuration with a previous one. If our new one is better by some unspecified means, then we'll add it to our chain. If it's poorer, let's say in the next step, then we'll stick with our old configuration. And then by recursing, this procedure continues, building up this chain of configurations. Okay, so I've described to you Metropolis-Hastings as this abstract program. To derive an algorithm from it, you need to provide two things. You give a semantics for the model interpreter and a semantics for the inference operations. So for instance, let's derive an algorithm called independence metropolis. So we'll begin with the model semantics. To handle observe, we're going to use the likelihood handler from before just to sum over the log probabilities of the model. For sample, we're going to define a new handler that will execute our model under a trace. So a detail I didn't mention is that each sample comes with a unique address alpha. If our trace contains a value for alpha, then we'll reuse it to draw the same sample. And otherwise, we'll get a new random sample out and store it in our trace. Next, we'll define the semantics for the inference operations. So when we propose, we're going to do something very simple and just map random values across our entire trace. When we accept, we'll compute the likelihood ratio between the new and previous weights. If this is greater than some random point between 0 and 1, then great, this is good enough, and so we'll accept it. Finally, if we then slot in both of these handlers to our inference pattern, we fully implement independence metropolis. So if I were to run this on linear regression, we get back the following graphs. And this shows that we prefer to accept samples around m equals 3 and c equals 0, which is great because these were the values we were expecting. But if you notice, we aren't actually accepting many new samples. And this is because when we propose, we're effectively generating an entirely new trace. And so the chance of this trace being accepted depends on all of our new samples being collectively better than our old ones. One solution to this is single-site Metropolis, which you can derive in the exact same way just by swapping around some parts. So here, I've just changed the type of our weights, how we execute the model, and how we propose and accept. So the key difference is in how we propose. So here, I'm only going to generate one new sample R for some random address alpha, and we'll keep the rest of the trace exactly the same. So the chance of this being accepted then comes down to this one sample being better than our previous one. So if I instead run this on linear regression, on the right-hand side, you can now see that we accept far more samples for C especially. Okay, so I've shown you how you can derive two concrete algorithms from the same abstract program for Metropolis-Hastings. Well, the same idea holds for particle filters, which you can also think of as programs with abstract operations. So let's have a look at how this works. It's a bit more interesting than Metropolis-Hastings. So a particle filter begins with a model and a weight, which we then create multiple clones of. Each of these clones is called a particle. We then begin the algorithm by applying PF step. So the idea here is that we're going to step through each particle's execution in parallel. So we do this by first mapping step over our particles. So step is a model interpreter. It takes a particle and its weight, and it executes it, but only up to the next observe operation. It then returns us a suspended particle and an updated weight. Next, we'll check if all of our particles have finished executing. If they have, then great, we can return their results. Otherwise, we'll call resample on them. So the goal of resampling is to filter out particles that are less likely. So for instance, resampling might produce this, where lower weighted particles are discarded entirely and higher weighted particles are cloned. Finally, by recursing, this procedure of stepping and resampling continues, and at the end we should get back a bunch of particles that are likely to produce our observations. Okay, so I've described to you a particle filter as an abstract program. To derive an algorithm from it, you follow the usual steps. You give a semantics for the model interpreter and a semantics for the inference operations. So one simple algorithm is called a multinomial particle filter. So we'll begin with the model semantics. For sample, we'll just have our particles draw a new random sample each time. Observe is more interesting because now we want to suspend our particles at the next observation. Well, this is easy using algebraic effects because we can access the continuation k. So when we match on observe, we'll now use k to return the rest of the program. However, this time we're going to return it as a value and we're not going to handle it. This hence represents the suspended particle. Next, we'll define the semantics for resampling. So given a list of particles and their weights, we'll first make a discrete distribution over the positive integers. The numbers that we get back are the positions of the particles we'll continue executing. We can then extract these particles and pair them with the average weight. And then finally, by slotting both of these handlers to our inference pattern, we fully implement the multinomial particle filter. So if I were to run this, say, using 100 particles on linear regression, we'd get back 100 samples of M and C. So something weird is happening here. It's not that our samples of M and C are bad, but they're all the same. And this is happening when we're resampling. So in particular, when one particle has a far higher weight than the others, we can end up cloning that same particle over and over again, which limits the results we get back from inference. The last algorithm I'm going to talk about tries to improve on this exact problem, and it's called Resample Move Particle Filter. The idea is that after resampling, we're going to apply Metropolis-Hastings to each particle. This is going to propose new sample traces for them and effectively move around the samples that they've already drawn. So we can derive this algorithm in the exact same way I've shown you already. So to support Metropolis-Hastings, we'll now execute each particle under a trace. The interesting bit is how we resample. So here, I'm going to keep track of an integer t, which counts how many observations we've seen so far. We'll begin by resampling, exactly like the previous algorithm, except this time, we're resampling the particles' traces rather than the particles themselves. Then I'll use something called suspend after. This takes the original model and it returns us a new version that suspends at observation t. So the reason I'm doing this will become clear in the next step, where we'll use it to apply Metropolis-Hastings to each resampled trace. The result we get back is a partial trace containing new samples up to point t and a particle that resumes from that point. And this fully gives us the resample move particle filter. So if I instead run this on linear regression, on the right-hand side, you can see that the particles we get back are really rich in terms of their results now. Okay, so to recap, I've shown you a new approach to enabling programmable inference. I've used abstract operations to reveal how the algorithms are structured, and I've used effect handlers as a way of programming them. So if you recall, there were three things that I thought were quite important for inference programming. The first was being able to reinterpret how models execute. So there are many ways of going about this. Some let you program your own execution, some give you a selection to choose from, and some can't be programmed at all. The second thing we cared about was being able to build new algorithms out of reusable parts. The most obvious way to go about this is to use functions. And while functions are super modular, modularity isn't the only thing we care about. For inference to be easy to program, it can be useful to have stronger abstractions, ones that make it clear how the algorithms are structured and how they can be extended. The last thing we cared about were types. This is the wrong room to preach about why types are important, but I think this becomes especially emphasized for designing inference, where we need to manage all of the messy side effects and imperative baggage that the algorithms come with. Typed functional languages like Haskell give us a really solid foundation for all of these aspects. And this was shown by a really cool language called Monad Bayes, which used a monad transformer approach for going about this. However, Haskell and probabilistic inference are individually quite hard, and intersecting them can have a really steep learning curve, especially when we start involving monad transformers. In this talk, I wanted to explore how effect handlers can provide perhaps a more intuitive or at least a more explicit interface for the average programmer, which still builds on the ideas of composition and type safety that we really care about. Thank you so much for your time.
Yeah, thank you very much. We have time for maybe one, maybe two questions, so please.
Hi, I'm Alexei Radl from Google. Great talk. I've messed with this in the past, so separating models from inference algorithms is very dear to my heart. Can this framework implement a Gibbs sampler?
Implement?
A Gibbs sampler. The essential feature is that the proposal depends on the continuation of the model to propose from the local posterior.
So I think a Gibbs network, that would require a static representation of a model, as in you would need to know the entire model statically. So I've tried very hard, and I haven't managed to do so. And I think that's the end of my answer to that. So I'm not sure is my honest answer.
Any other questions? If not, then let's thank the speaker one more time. Thank you very much.